Welcome to the semi-learned lecture on Pareto's famous 80-20 rule and how it relates to the phenomena of 10x software developers. Our story starts in the vegetable garden of Vilfredo Pareto at the end of the 19th century. He's harvesting his crops of peas when he noticed something strange. Very few pods like these ones were very full of peas, but the majority of the pods had very small number of peas. Now, having a bent on statistics, Pareto actually counted how many peas were in each pea pod and found that 20% of all pods accounted for 80% of the peas he harvested. And that meant that the remaining 80% of the pods only produced 20% of the peas. Now, Pareto was a civil engineer by training, but a polymath by nature, and so he decided to explore whether this 80-20 distribution manifests itself in other areas other than peas. And because Pareto happened to be enamored by economics at that time, he investigated whether this 80-20 observation applied to human wealth. And indeed, he found that 80% of the land in Italy was owned by 20% of the population, and therefore the remaining 20% of the land was owned by a much larger 80% of the population. This got Pareto, and later others, to wonder if there is an 80-20 rule that applies to all other human endeavors. And although the 80-20 rule is not a law of physics or mathematics in that it cannot be proven by a theory, it was indeed found to represent various aspects of human activities. For example, in his book The 80-20 Principle, Richard Koch informs us that 80% of retail sales are due to 20% of the customers, and that 20% of players on a sports team contributes 80% of the goals or the points that the team scores. And even in medicine, we find that 20% of the patients take up 80% of the attention and time. More interesting findings are revealed in The Tipping Point, where Malcolm Gladwell informs us that 80% of the work is accomplished by 20% of the participants. This fact gives rise to the alternative name for Pareto's 80-20 rule. It is often called the rule of the vital few. The rule implies that when building a team, if one targets that 20% pool of high achievers, then one can create super productive teams and corporations. And nowhere is the rule of the vital few more apparent than in the area of software development. There we find a widely accepted view that if the productivity of a typical software developer is represented as 1x, then there exists a small group of vital few developers whose productivity is 5 times that of the average developer. These are known as the 5x developers, or 5xers for short. And indeed, there is even a smaller number of highly sought-after 10xers whose productivity is 10 times that of the average developer. Now, unfortunately, many teams think that they can circumvent the rule of the vital few by hiring many lower-paid 1x developers versus a few higher-paid 5xers or even 10xers, hoping that, in the words of Joseph Stalin, quantity has a quality all of its own. But does that approach really work? Let me illustrate to you the fallacy of this thinking with a personal story. Back in my high school days, our class was assigned a rather difficult programming problem to solve. It took me hours of deep thought to solve it, but at the end, I had this very elegant and simple solution to the problem. It was encapsulated in just one line of code. Now contrast me with my friend Nicholas, who only needed 5 minutes of deep thought over lunch on the day that the assignment was due to come up with that same very elegant solution that took me hours to formulate. Clearly, Nicholas was a 10xer, whereas I was, well, let's not go into that. But taking a less anecdotal approach, we can actually quantify the impact of the high X workers on both the budget and on the duration of any project. First, from a budget perspective, we find that as the value of X increases, the remuneration per developer does not rise linearly. For example, if a 1x developer costs us 1 unit of budget, then a 5x developer may only cost us 2 units of budget, and a 10x developer may only cost us 4 units of budget. So clearly, hiring developers with higher X factor can actually reduce the overall project budget, if one is able to find them and hire them. Next, we're going to explore the impact of the high X developers on the duration of a project through the lens of Amdahl's law. Now, back in 1968, Jean Amdahl stated that any project is composed of 2 types of tasks: parallelizable tasks and serial tasks. Now, parallelizable tasks are those that are usually easy to accomplish and that are also easily subdivided into multiple subtasks that do not depend on each other. For example, the task of washing all 4 tires on a car is a simple task that is easy to parallelize. A team of 4 people can each wash 1 tire, and if they all do the washing at the same time, the duration of the job decreases by a factor of 4. On the other hand, serial tasks cannot be divided between many workers. They can only be assigned to a single worker. An example of a serial task is changing 1 flat tire on a road. It is composed of a sequence of serial tasks that cannot be performed in parallel. First, the tire nuts have to be loosened, then the car has to be raised using a jack, next the tire has to be removed, then replaced with a new tire, etc., etc. Even if we had more than 1 worker available, the sequential nature of the subtasks means that no 2 subtasks can be completed at the same time. So having 1 worker or 2 workers will not impact the duration of the tire replacement tasks. Having 2 people involved will not replace the tire in half the time. However, if I had a very skilled worker who is twice as fast as the average worker when it comes to changing tires, then the duration of the serial task may indeed shrink by a factor of 2. Another often cited example of a serial task is the bringing of a new baby into life. 9 women cannot create a baby in 1 month, and adding more women to the task will not make it happen any faster. Childbirth is the ultimate serial task in that it can only be done by 1 person and it will take approximately 9 months to complete. Fortunately, other types of serial tasks, like changing the tire of a car, can be accelerated either by hiring workers with a natural skill or giving them appropriate training. Those would be the high-X tire changers. And Amdahl's law expresses these concepts of serial and parallelizable tasks using very simple mathematics. Let's assume that the duration of the entire project was 1 unit of time, and that the fraction of time spent on the parallelizable tasks was p. It follows that the fraction of time spent on the serial tasks would be 1 minus p. When parallelizable tasks, like washing the tires, are subdivided into multiple subtasks that do not depend on each other, each one of these subtasks can be assigned to one of many 1xers, and working in parallel, it takes the group of n 1xers a shorter amount of time to complete all the parallelizable tasks. If the duration of the parallelizable task was p, applying n 1x developers reduces the duration to p divided by n. On the other hand, serial tasks cannot be divided between workers and can only be assigned to a single worker. Assuming that this worker happens to be a 1xer, then the duration to complete the serial task will be unchanged, remaining equal to 1 minus p. So the overall new duration of this project becomes the sum of the unchanged serial tasks and the much reduced parallelizable tasks. This will be less than the 1 unit of time, which was the original duration, and we can add more 1x developers to the parallelizable tasks to make the duration of these tasks even smaller. But the duration of the overall project becomes increasingly dominated by the serial tasks that can only be assigned to 1 developer at a time. Now, if we go and hire a 10x developer who can finish the serial tasks much faster than a typical 1x developer, then the duration of the serial task shrinks from its original time to that original time divided by x, where x is 10 if we hire a 10x developer, or 5 if we hired a 5x developer. This changes the overall duration of the project, which will be the sum of the much reduced serial task and the previously reduced parallel tasks. By hiring just that 1x developer, we have significantly reduced the overall project duration in a way that no additional number of 1x developers would have done. We delve more into the dynamics of this in our semi-learned lecture on Amdahl's law, and the link for that lecture is in the description section below. And so, Amdahl's law shows us that we cannot just depend on increasing the quantity of the 1x developers, and instead we need a mix of both quantity and high-quality high-x developers. Now this raises a question about what mix of developers do we need to have for a given project. That is not an easy question to answer because it depends on the nature of the project. For example, when I used to be part of a large team building complex digital silicon chips, the projects had many parallelizable tasks that could be easily divided up between many 1x developers. So the distribution of the X mix for the project tended towards a majority of 1x and 2x developers with fewer high-x developers for very difficult serial tasks. Now sometimes these digital chips really got complicated and we had to increase the number of high-x contributors to complete the project on time, but the distribution was still weighed towards the lower X developers. When I moved on to developing compilers for machine learning networks, the number of difficult serial tasks became a higher percentage of the work, and the team that I assembled for the task, shown here in the blue line, contained a higher number of members that were in the 3x or above category. If the team had not included a larger number of high-x developers, we would have probably failed to create a competitive product that outperformed our competitors. Finally, if the project at hand was a very complex project, like developing a super intelligent AI model, as represented by the red line in this graph, we would need a team where most of the members were close to the 10x class of developers. The key takeaway here is that no single X mix fits all projects. Every project type will have its own ideal mix of developer capabilities. We just need to ensure that we have a sufficient number of high-X developers to succeed. And that brings us to the end of this semi-learned lecture. To explore Amdahl's law in more depth, follow the link that we have in the description box below. We thank you and wish you all the best.